Thank you. Thank you all for coming to this session. I'm Luigi Nardi. I'm a founder and CEO of dbTune. Today we'll be talking about a benchmark study on the impact of Postgres server parameter tuning. I have very fond memories of this event. I was here 3 years ago and I gave a tutorial on server parameter tuning in one of the rooms in the building. This is a picture of the event back then. I was curious to know if there is anyone that recognizes themselves in the picture. I think it's at least one person in the room. Anybody else? Good. Right, so just very briefly about me. I have a mixed background in industry and academia. I have a PhD in computer science from La Sorbonne University and worked as a research staff at Stanford University before becoming an associate professor in artificial intelligence at Lund University. Since then, I left my academic endeavors and I'm running dbTune full-time now since 2020 when we incorporated. Very briefly about dbTune. This talk is not about dbTune, but I will just introduce the company for a couple of minutes before starting on the topic. This is an AI-powered database tuning service for server parameter tuning. It's a spin-off from Stanford University, and this is really the idea of taking Postgres, which is shipped usually as a general package, and trying to make this package really specific to you, your use case, and your load and machine. So customizing something that gets shipped in a fairly generic form to something that is specific to your use case. The big announcement that we're making here in Prague is that dbTune now supports cloud native PG. So if you guys run on cloud native PG, now you can also declaratively tune your cloud native PG, which is something that wasn't really possible until now. So we're basically moving cloud native PG one step forward in terms of like automating all sort of tasks, and this is the performance tuning task. There is a blog post co-written with Mohsin here, and this is the link in case you're curious and you want to check it out. dbTune has been part of the Postgres community for quite a few years. We've been big sponsors of this type of events. Here you can see our little name here on the chart. So we're very proud of that. That means we also organize a Postgres user group in the southern Sweden region. And I would like to invite you all, if you're coming to Sweden, to let us know if you have a good topic that you would like to discuss, of course, related to Postgres. But we're pretty, we like to have diverse type of talks. So if you have any talk and you would like to present it, please let us know that we will introduce you to the Postgres user group in Malmo and discuss options for you in terms of timeline and so on. Okay. All right. What is this talk about? The question that I hear quite a lot in this space is it worth tuning your server parameters? And there is a slight misunderstanding in the community that if you tune your parameters, you only get like this 5-10% improvement in performance. Okay? I will argue that if that statement was true, the Postgres team will basically remove those parameters, because why would you even bother if you have a 5 to 10% on the table by doing server parameter tuning? So in practice, this talk is really kind of to shed light on that. We will talk about some benchmarks, but we'll also talk about some real world applications and try to see what's at stake here. However, in this talk, you won't learn how to manually tune your Postgres instance. That's a lot of work. You need to go through the blog posts if you want, the docs, and so on. We will not talk about that. We'll really focus on what's the impact of server parameter tuning, and we will see that on a number of different applications. But before doing that, I will give a very short introduction about Postgres server parameter tuning. I will show a quantitative example and then talk a little bit about how we solve that problem today. and show results in terms of synthetic and production workloads. Even if the room is a little big, I would like to invite you to ask questions in case you have them on the fly without waiting until the end of the talk. So just raise your hand and we'll take the questions on the fly. So what is Postgres tuning? Okay, so the idea here is that you want to keep your database fit and responsive. Databases are very dynamic objects. They grow, they slow down, they change, they grow, then slow down over time. Not all workloads and machines are the same, of course. If you look at the cloud providers, they have so many different offers in terms of SKUs and so on. And the idea of tuning is really the idea of adapting a database to its current use case, load and machine. So when we talk about tuning, this is usually considered a little bit of a dark art, meaning that database administrator, but these days also developers take this task on their plate sometimes these days, so platform engineers and so on. And it's really this idea of sitting down, try to understand what's going on in the logs and try to figure out what's slowing down the system and fixing it, right? The problem is that you usually need to have quite a lot of performance optimization experience, and this is considered a little bit of a hard task because you need to have all this wealth of experience before feeling comfortable changing something in a production system that can have impact on the performance. When we talk about tuning, we usually talk about several categories of tuning, and I think this describes the spectrum. We have query tuning, server parameter tuning, index tuning, operating system parameter tuning, and even schema design and things like that. That it's kind of part of this somehow. And other things. So today we will really focus on the server parameter tuning part. That doesn't mean that the other things are not important. They are all very, very important. There was another talk on indices, for example, this morning. So you saw that type of topic, and it's absolutely crucial to do all those things. But today we will focus on the server parameter tuning, which is, I think, the topic that I was describing at the beginning, being a little contentious. Changing work mem, how much can I expect from that? 5%, 10%, is that really just that? Why do we care then, right? So if it's just that. And hopefully I will make the point that it's not that little and there is a little more on the table at stake at least. So there is, of course, the technical perspective. I will not talk very much about the business perspective. Of course, when, as an engineer, I always like the second side here because I care about the first side. And this is a way for us to become heroes with the finance department, where we maybe make things more stable. And there is, of course, an effect on how much money a company makes if you run your database in a very smooth way. And there is the aspect of not over-provisioning the instances, which very often is the case. If you don't tune your system, you may need a machine size which is double the size, for example. And so if you tune your system, you can shrink that instance to what you actually need, so you don't pay double the cost on a cloud provider, for example, and things like that. And there is, of course, the reduction of downtimes aspect, right? So if your system is tuned, you will have less calls, maybe on a weekend or an evening, where there is an issue with the performance that needs to be fixed right away. Because the system is tuned, you have fewer of those problems over time. All right, so let's dig at this question of Postgres server parameter tuning. What are we actually talking about, a little more precisely? So this is really the idea of having a number of knobs and trying to find the best combination of these knobs in a way that performance goes up. I really like this picture here. It's an audio board, and you have all these different levers and knobs, and you're basically trying to find the best sound of the music that comes out of that. Similarly, in Postgres, you're trying to find the best combination of these parameters in a way that you achieve this higher performance, right? The parameters that we usually talk about in Postgres are this type of parameters: work mem, shared buffers, max world size. Those are the parameters that usually you see in blog posts and so on. So here, for example, define one, which is max parallel workers per gather. And this is a parallelism parameter. There are multiple parallelism parameters in Postgres. This is one of them. And this is specifically, I will call it the intra-parallelism parameter. So if you have a complex query, this is the parameter that helps decide how many workers should work in parallel on that query, right? Just put it simple. There are parameters that are related to memory as well, or disk. And so this random page cost, for example, is a parameter that influences the query planner. And the way it does that is by defining the planner's cost of a non-sequentially fetched disk page. Okay, so this is related to the disk, but this parameter directly affects the planner. Right, so if we look at how these parameters should be tuned, this is highly dependent on the application. So you cannot just tune this for one application and then reuse the same results for another application, because this will not work very well. Imagine the most simple of these examples will be if you have a read-heavy workload and then you have a write-heavy workload over there. So you cannot just use the same configuration of the server. You need to specialize the solution for the application in hand. So in the next slide, I will just show an example of this application-specific type of aspect. Here, I'm using a benchmark called opinions.com. This is a product, so it's a product review system. So it's an OLTP type of workload. You can download it from the internet. So this is an open source benchmark, part of the Benchbase benchmarking suite. And here I'm showing two axes. The first parameter is max parallel workers per gather, which I introduced before, and random page cost on the other axis. Okay. Here I'm doing the most basic tuning that can be done. I'm just basically doing exhaustive search on just these two parameters. Okay. I basically try all possible combinations of the Cartesian product of these two parameters. Okay. And very often you cannot do this exhaustive search, but since here we only have two parameters, I'm doing that, okay? And on the vertical axis, we have the query runtime in milliseconds, so lower the better. And so if you look at this picture, you see the colors, and the dark blue will be the best solution, and the yellow will be the worst solution. Okay, so this means for this opinions application, having parallelism actually hurts you. You don't want to have multiple workers working on this queries. Having a random page cost which is small is good for you. Okay, so the combination of random page cost and small max parallel workers per gather, it's good for you. Okay, and so if we look at the y-axis, sorry, the vertical axis, we can already notice that there is a pretty big difference between doing it well and doing it poorly. So there is this kind of order of magnitude difference between the sub-millisecond on the bottom right corner, and the yellow is 8 milliseconds or so. So there is already a pretty big gap in between the dark blue and the yellow. So this is the first thing that we learned from this very simple example. If we move to a second example, TPCH, which is a pretty popular benchmark, again, open source, you can download it from the internet. And if you look at the shape of this, you see that the kind of performance on the table, again, from doing it well and doing poorly, it's again roughly an order of magnitude performance on the table there. The interesting thing, though, is that if Thomas comes with opinions and I give him the solution of the bottom right, which is low random page cost and low max parallel workers, and then Mayuresh comes to me with the TPCH and I give him the same solution, well, I'm not treating Mayuresh very fairly, because I'm literally giving him the worst solution I can give him, because I will give him the bottom right of TPCH, which is the yellow part. So I'm giving Mayuresh the worst possible solution by just trying to get the solution they got from this application and replicating it to this other application, right? So this makes the point that this needs to be application specific. And so you need to do the tuning if there is another application, or if the application has changed over time. So the first thing that we learned from these two plots is that there is this pretty significant performance on the table. The second thing is that this is really application specific. And there is a third thing that we don't learn directly from this, perhaps, but it's usually there. Database administrators, when they do tuning, they do this sequential scan of the different parameters. They start with one parameter, and then they move to the second parameter, third parameter, and so on. But very rarely they go back and change holistically all of them at the same time. And so, sometimes this happens, but it's very hard because it's a very large optimization space. If you optimize in a sequential manner all these parameters, though, you're missing potentially a big opportunity, because that basically means that you're moving in a parallel fashion on this axis, and you may miss the the diagonal kind of gradient descent type of thing, right? So you may miss the dark blue because you're moving like this. You will never meet the best part of the space. So these are the three things that kind of appear when we look at this type of benchmarks. So if we look at the complexity of this over time, we see that the number of parameters are increasing. I think there was a talk by Joseph the other day. He had 400 parameters in Postgres 18. Yes, my estimates are roughly the same. Not all those parameters are important for performance tuning. Let's say that very clearly. And in practice, my guess is that perhaps between 20 and 25 parameters really matter for performance tuning. And all the rest of the parameters are just not important. Like if there is a file name as a parameter, you need to define a log file name, that will not affect the performance of the system, right? So that doesn't matter, right? But let's say 20 to 25 parameters are important for performance in Postgres. What does it mean though? So if you just consider just 12 parameters, and I took 12 in a slightly random fashion, maybe here, but 12 already gives you this kind of 1 trillion possible configurations of the system. So it becomes a very large space, even with just the 12 parameters. And the other aspect is that when you add one parameter, this doesn't become a little harder. It becomes exponentially harder because it's a combinatorial thing. So if you add one parameter, you're adding much more potential, optimization space, basically, right? And this is shown by the fact that the curve goes like this exponentially, right? So we need to be really, really careful in Postgres adding new parameters. At the same time, the Postgres community has been really, really wise over time and observing the usage of these parameters over the years. And sometimes some parameters disappear because they've seen that they don't have an impact, and so they've removed them from the list of parameters, which is really great because it's easier then to use Postgres if there are fewer parameters. Okay, so those that are there, there is a common wisdom on the fact that those have an impact, and that's why they're there. Otherwise, they will be removed, right? All right, so how is parameter tuning tackled today? This is something that it's often done manually. The process of manual tuning is a little slow and takes a little time. I have the picture of our colleague Magnus Hagander here. I could have replaced this with some of you, in the room. My tuning guru, right? So the person I would go and ask any questions about tuning. Magnus has been in this space for 20 years. He knows really well how to tune all sorts of knobs. But these people are a little difficult to find, and it's also limited in scope because workloads tend to change over time. You develop new features in an application, and then you end up having a workload that is a little different, let's say. So there are other solutions like heuristics, and if you didn't use things like a PGTune or Postgres configurator, I would certainly recommend that you guys try it out, because I have it in the next slide where I will talk a little bit about those. The risk, though, is that the heuristics are a little fixed in the sense that they use fixed rules and they don't fully adjust to your specific workload and use case, but they're still very good, and they give you a big jump in performance from your baseline usually. So there is a third solution, which is the AI approach. So this is a talk that's not about dbTune, so I will not talk very much about this, but this is the idea of having an agent that learns by observation and adapts to changing workloads, automatically tuning and under minimal supervision. The reason why I'm talking about this here is that I'm too lazy to do this manually, so all the experiments that you will see afterwards, I will just use this to produce the results, right? I will not do all the work manually, okay? But before getting there, the heuristics-based server parameter tuning, we have this couple of options here. As you can see, they're extremely simple to use. It's just a web interface. For PG tuning, you also have the source code. You can use directly the source code. You insert, the database version, Postgres version, a couple of pieces of information, and you just the RAM size and this how many CPUs you have. You push a button, and this gives you the configuration file that you can then basically copy paste in your pgconf, and you're done. Similarly with CyberTech Postgres configurator, it works very similarly to that as well. All right, so this is how we will set up the experiments. So we have this Postgres instance on the left, and then we have this agent that basically tunes the instance. And then there is this optimizer as a service in the cloud, and it's basically sending the recommendations. The recommendations are applied, measured, and then there is another loop for this until this converges to the optimal configuration. So the whole process lasts maybe 3 or 4 hours, and this is how we tune the benchmarks that I will show in a minute. There is this question on how often do you tune, and again here the common understanding in the community is that you do this once in a year or something like that. But things are becoming quite dynamic these days, especially in the cloud era. And applications are changing quite dramatically sometimes with new releases, new major releases, and so on. And so I will kind of create 2 buckets. There is the ongoing requirements where you're scaling your instance up and down. For example, if you're moving from an instance that has 4 cores to an instance that has 8 cores, you technically change the hardware, so you may want to tune again that instance. If your application workload is changing, big release, the team is releasing a bunch of features, this may affect the workload and the way it runs on the machine. And there is this more subtle thing. I think that there have been also some talks in the past. I think Thomas had a talk where he was showing this sudden performance change in an application when you moved from 1,000 rows to 1,001 rows or something like that. I can't remember the exact details. But changing the tables, that changes the statistics. And if you change the statistics, the planner will change as well. And the planner changes in Postgres without telling you, right? And that means that if you change the statistics basically by just using Postgres, at some point the planner may change. And if the planner changes, it means that the queries are executed in a different way. And that means that your performance may get worse or better, right? But it's possible that you would get affected there. And so if this happens, sometimes tuning can really bring things back to normal. And of course, there are some very specific moments, like you tune when you move from Oracle to Postgres. I mean, it's pretty obvious if you're moving from on-prem to the cloud, or vice versa. These days, it's not that uncommon anymore. You're migrating from Postgres version, for example, or you experience downtimes. And these are all the scenarios where you will think about tuning, for example. So I will argue that looking at this list, it's a little naive to think that you tune once and then you forget, right? Because these are situations that may arise maybe once, twice, 3 times, maybe a few times a year. And so it's good to think about that and keep your instances well tuned. Okay, I will just skip this and go into the slightly more interesting part. So these are the parameters that we will tune today in the experiments. We have about 15 parameters in total. I'm not listing them all here. If you want to find the whole list, is in this link over here. And if you would like to learn a little more about these parameters, what they mean, there is this blog post written by Mark Linster that talks a little bit about these different categories of parameters. But very briefly, that talks about these 4 categories. There is the disk category, there is the memory category, there is the CPU category, and then there is the planner category, right? So those are the 4 things. And if you go back to your 101 CS computer science class, it's kind of trying to tackle the von Neumann machine, right? So the idea of you have the I/O and you have the the memory and CPU, and trying to basically make the data flow from disk to the registers of the CPU in a very smooth fashion, so you don't spill to disk and you can effectively use the resources of the machine. All right, so let's get into the benchmarking side of this. So the first set of results are on HammerDB, which is a pretty popular benchmark suite. It's called benchmark suite because there are 2 benchmarks in this benchmark suite. When it's more than one, it's called the suite. And here in this case, we are testing on TPCC. This is the most obvious starting point because TPCC has been used for, 20 years. It's a very old benchmark, so I don't really care very much about TPCC, but since it's a benchmarking exercise, we need to have TPCC in the slides, and that's why it's here. There is a blog post written by Mohsin here, and Steve Shaw, that was the author of HammerDB, where they worked on these experiments. TPCC, you can see it's a wholesale suppliers order and delivery operations across multiple warehouses. So it's a OLTP write-heavy workload. The first point I would like to make is that another kind of misconception in the community is that if you want to do benchmarking, what you do is to download the benchmark, run it, and you're done. Unfortunately, benchmarking is kind of a hard science, and it's really, really difficult to run benchmarks in a way that it makes sense. And I would like to explain what I mean by that. So if you look at, for example, the best practice, for example, it's the best practice of running a benchmark is to have the workload running on a node and then running the database on another node. And then, of course, here we have the DBTune agent that does the tuning, but that's a detail, okay? So you have this two-node architecture if you want to run the benchmark properly, and you shouldn't run both of them on the same node, because otherwise you create all this interference between the things, and this wouldn't be as realistic as you wish. When you're trying to do benchmarking, you're trying to be realistic, and a production system looks much closer to this than running everything in the same node. Think about if you're doing PG bench, a little experimentation, you run everything in one machine. But if you're doing real benchmarking, you should have a distributed setting like this. And things become a little more complex when you do this already, right? So it's more complex than just running on one node. This is the machine used for these experiments, but these are details. We can skip those. The second thing, again, downloading HammerDB and running it just out of the box will not create a benchmarking realistic setting, okay? So for example, HammerDB, I think is really by default just running for 5 minutes. So a benchmark that runs for 5 minutes. Can you gather, all this effect of having caches that are cold, for example? Would that 5 minutes be enough to warm up the caches? If you don't warm up the caches, does it even make sense, the performance numbers that you're getting back? Probably not. So you need to, first of all, increase the time for the duration of the benchmark. So there is a very simple command that you can do, but you need to do it. It's up to you to do it, right? And if you do this, then you create this sustained load, and the caches are warm once that you start the measurements. There is the second aspect, which is the number of warehouses. And I think the default is much smaller than what you should have in a current size machine, in a modern machine. So it's, again, up to you to create a workload that is a little more realistic. And there are some guidance on the HammerDB website. Here we brought them up to 500 per CPU socket. And the second point also means that we are now 52 gigabytes of data volume from the beginning. And that's important because you don't want to have a benchmark that it fits entirely in your RAM. Because if you do that, again, you're not doing benchmarking in a realistic scenario. So if there is no need to go to disk, what kind of performance benchmark are you actually creating, right? So you need to have a data volume that doesn't fit in RAM. It needs to be at least maybe twice as big as the RAM that you have on the machine, okay? So these are all little nitty-gritty details that are really kind of important to define a benchmark that makes sense. Because if you don't do these things, and for example, your benchmark fits entirely in RAM, then if you go, for example, tune some disk parameters and they don't have any effect, then the conclusion is, oh, this parameter doesn't have any effect. Let me write a blog post that says that this parameter doesn't have any effect. But that's perhaps because you didn't stress the system in a way that it's realistic, and that parameter can really show the effect of making a good decision, right? All right, so a couple of other things there to set up TPCC on HammerDB. The other aspect that is really not very well understood about HammerDB is the following. So here I'm showing a plot on the x-axis, you have time, and on the y-axis, you have the database size. So if you run HammerDB for the first, at the beginning, we're talking about the 52 gigabyte footprint that I was describing before. But since it's a write-heavy workload, what this gives you is this massive increase in the database size in a very short amount of time. And this, again, it's a pretty unrealistic scenario. So I don't think that your databases grow 7% every hour or so, right? I don't think that's realistic. So again, if you want to put yourself in a scenario where the benchmark runs in a realistic fashion and you can drive conclusions out of that, you also need to take care of this, right? A more realistic growth would be maybe 2%, which is already quite aggressive, right? But even 1% will be a even more realistic scenario. The good news is that if you run HammerDB for just a few hours, then you see that the growth rate goes down to 2.5%. And this starts to be a little more realistic. So if you're setting up HammerDB for your experiments, make sure that the data volume doesn't fit all in RAM. Make sure that you set up the number of warehouses to the right values. And make sure that you run this long enough that this database size doesn't grow like more than like 2 or 3 percentage points, right? So the setup for the experiments then are like this. We did all of these things, and then we wait for, I think, about 12 hours before starting the tuning so that the system has all these properties, and they look a little more realistic in terms of looking more similar to a production-like system, right? So here it's a first set of results. Here we compare the tuning with the PG tune and the Postgres defaults. So the left-hand side, we have a comparison against PG tune. And here on the right-hand side, we have a comparison against the Postgres defaults. So this is measured in speed up. So speed up is usually above 1, and 2x speed up roughly means that you have double the performance of the system. So this is kind of the results that we see on one of the most tuned benchmarks that exist. TPCC is one of the benchmarks that everybody uses to do some sort of like tuning. And even in that case, which is a pretty simplistic synthetic benchmark, you still get this potential 2x improvement in performance if you do it well. But what is also interesting here is that PGTune already gives you this pretty neat improvement in performance of 1.55x from this baseline here. Sorry, this one is the reloads only, and this one is with these 2 parameters for the restarts, and so the performance can go all the way up to 2. Or in this case, from Postgres defaults, it's 1.82 and 2.14x. So on TPCC, this is a pretty interesting result, very well organized and set up type of benchmark, and we already starting to see the type of performance on the table that is available. So moving on some other benchmarks. So here I'm using some other benchmarks. I will not have the time to explain all these benchmarks in very much details, but Resource Stressor, and those are benchmarks that we have in the Benchbase benchmarking suite, TPCH, opinions.com, and Seats. So these are some other benchmarks you can download from the internet. Again, for these benchmarks, you need to, again, configure the benchmark to make it make sense. For example, the skill factor tells you the size of the database. And so if you use a very small skill factor, again, that means that your benchmark will fit in RAM, and then you're not doing benchmarking properly, right? The number of terminals, the duration of the benchmark, there are a few parameters like this that you should really set up before running these benchmarks. The rest of the benchmark is publicly available, but if you're doing realistic benchmarking, you should certainly take care of these parameters before you drive any conclusions. And this is an example here on the bottom of how we set up opinions, for example. So this is the performance results on these 3 benchmarks, the Resource Stressor, TPCH, and opinions. You can see here, for example, that we go, this is in milliseconds, and we are optimizing for average query runtime. Here, with Resource Stressor, we're moving from a 10 millisecond to all the way down to perhaps 2 milliseconds or 1.8 milliseconds. TPCH, and that's maybe a 6 or 7x improvement in performance. TPCH is a little more conservative in terms of performance that you can get, but we're still talking about a 2x on the table. And opinions, we have this 5x type of performance on the table. So all these results show that the performance on the table is much more than just 5 to 10% from the baseline. But of course, it all depends on the baseline as well. So it's if right before someone has just tuned the system, then the performance that you expect maybe a day after is much smaller than this type of numbers, right? Let's move into some more realistic examples, production system type of examples, because I think these are the most realistic and most interesting ones. So I'm getting some customer data, anonymized data here. This is an insurance application use case study on a decently large machine, 16 virtual CPUs and 32 gigabytes of RAM on PG15. So this is interesting because this was manually tuned, but this really shows that there is much more performance that you can squeeze if instead of spending maybe just half a day on tuning, you spend a more significant amount of time. So here we use this automation agent that we created to do this, and we go from the baseline, which is the manually tuned baseline at 0.85 milliseconds, all the way down to 0.34 milliseconds. This is roughly a 2.5x improvement in performance on a production system. And I can tell you that the database administrator did this manually was very, very surprised that there is so much more headroom for performance on an application like this, because he has been fiddling with those parameters quite significantly, right? Another example, this was from RDS on a pretty large machine, 32 CPUs with 128 gigabytes of RAM on a Postgres 17.6. This was a baseline by RDS. If you're running on RDS, the defaults are pretty bad. So if you're running on Postgres defaults on RDS, I would highly recommend to check that out, because you're probably leaving quite a lot of performance on the table. I think when you do tuning, the interesting part is that for this tuning, for example, this went from 100% to 50%. So these are not numbers that you can, not milliseconds, but this is going double the performance on a production system. But the second bar, I think, is even more interesting, because the tuning, what it does is not just to improve the performance of the system, but it's also to kind of make the instance overall healthier. Healthier here means that the CPU utilization goes from 80% to 30-50%, which is kind of almost halving the CPU usage. So by tuning the average query runtime, you can also get this better CPU utilization. And it kind of makes sense, right? Because the average query runtime is a proxy for the overall kind of health of the system as well, right? So if you tune the response time, you can get this type of CPU utilization improvement for free as well. So this is another example of a production system that is pretty interesting. The last one is on an even more complex instance. This is a 48 CPU with almost alpha gigabyte of RAM on a Postgres 14.17. This baseline, again, was from RDS. And we see that here, for example, you have this 10x jump in performance after tuning. And I will argue that the more complex the system becomes, the more benefits you get from tuning. So again, if you think about the statement that it's common in the Postgres community, which is you can get 10% performance improvement with parameter tuning, that's often the case if you're running a PG bench on your laptop machine on a very small data volume. I agree with that. I agree with that statement. But when you move into a production system, and this is a very heavily used system with 48 CPUs and alpha terabyte of RAM and a very complex environment, that's really where a lot of the bottlenecks really arise. And if you do the tuning there, you can get this massive 10x improvement in performance, right? So you will not see this if you run on PG Bench on your laptop on a simplistic benchmark. All right, so conclusions and food for thought. So the realistic benchmarking thing is absolutely crucial. And I would really invite everybody here to think about this if they're running any benchmarking results. Benchmarking is really hard. So if you're doing something quick and dirty, you cannot make general statements about this. If you're willing to spend a significant amount of time to understand the benchmarks and setting them up in a way that is distributed, as I said before, on these two nodes, that is the right data volume and the right configuration of the benchmark so that it makes for a realistic benchmark, then you will need to invest a little bit of time. And I would love for this type of conference to see more benchmarking, because benchmarks historically have been this thing that really help people to drive conclusions. So if we don't do realistic benchmarking, we don't drive the right conclusions. It's as simple as that, right? And of course, the benchmarking depends on the SKU, right, that you're using, smaller instances and bigger instances and so on. Right, so I think I have covered that part. Right, so the final thing here is that the speed up that you get when you do tuning really depends also on the baseline. So the baseline of the Postgres defaults is conservative. I don't want to use the word bad because it's not bad per se. It's just made for any sort of machine, also a very small form factor machine, right? So they need to be conservative. But if you start from that baseline, well, the performance on the table is an order of magnitude, right? If you start from better baselines, the ones provided by the cloud providers, for example, perhaps the performance on the table is a little smaller. And if you do the manual tuning and you're an expert, perhaps there is a smaller headroom. But of course, you need to do the work manually in that case. Right, so I have covered all the material for today. I think I'm roughly on time. We have a couple of minutes for questions. I just want to mention that some of these results are in the dbtune and HammerDB blog posts that if you want to read. We also wrote a tutorial on how to run a synthetic workload. This was specific for dbtune, but the first part of the tutorial is generic to running benchmarks. So if you want to learn how to run benchmarks in a slightly more realistic manner, there is a GitHub tutorial there that shows how to run some of these experiments basically on bench-based benchmarks and so on. And that's all I have. Please feel free to connect with me on LinkedIn or shoot me an email if you have any questions on the content as well. Thank you.
Okay, so thank you for a very nice talk. Are there any questions? Okay, so there are two.
So thanks a lot for the talk. I want to know, how do you prevent overfitting during tuning? Because, for instance, the example that you showed in the beginning, the two different workloads were pushing the parameters into opposite directions. So let's say there is a different workload on my database on Monday and then on Tuesday, and then what happens if I tune on Monday? It sets parameters that are really bad for the Tuesday's workload.
Right, so that's a great question. So you're talking about a multi-workload scenario. You're talking about a system that sees a workload at a certain moment in time, and then it sees another workload at another moment in time. My question for you is, how would you manually tune that system? You would get some sort of average between the two workloads in a way that it works in average well for both of them, which basically means that you are basically creating a third workload, which is a mixture of the two, and you're tuning that one, right? Did I describe this well? If you're doing manual tuning, you also need to be careful that there are two workloads running at different moments of the week. And the way you will tune those is to basically tune the average use case. The average use case basically means that you're creating in your head a third workload, which is a mixture of the two, and that's the workload that you're tuning. The ideal setting will be to actually have a configuration for the workload number one and another configuration for the workload number two. So a better way of doing that will be to overfit, if I use your same word, for the workload number one, and then overfit for the I wouldn't call that overfitting, but I'm just trying to reuse your word. And you could, for example, tune, if you really know that things are so precise, you could just tune Monday and then you tune Tuesday. You get these two configuration files, and then you cron job them, right? Otherwise, you need to create this third workload, which is a mixture of the two, and then you need to focus on that one, right? I don't know if this answers your question. Okay.
Thank you for the talk. So for performance tuning, there is one more aspect that is simulating your production or application workload on test environment and trying to tune over there. So you were talking about benchmarks, but it's always better to benchmark your own application rather than depending on generalized benchmarks. So what do you think about that?
Right. So that's a great question. So if I understand correctly, the question is, of course, it's always better to benchmark your own production system instead of using common benchmarks. So in the results, I've shown some synthetic workloads, and those are completely fake or maybe inspired by some applications, but synthetic in nature. But I've also shown some production systems. But the angle that I was taking here is that we were really tuning directly the production system. There is, of course, another option, which is having tooling around tracing your database and creating a digital twin. And that you can think about that as a gym where you do all sorts of crazy things and you try to get this digital twin optimized, and then you take that solution and you bring it back in production system. The reality gap is what measure the difference between what happens in the digital twin and what happens in the production system. That's called reality gap in the machine learning community. And that reality gap is a serious thing, right? So if you do a very good job at recreating the digital twin in a way that is very close to your production system, then I think that's a really great thing because you can really tune the non-prod and then bring things back to the prod. But what is your experience doing that at a very good quality level? Right. So in general, we've seen, I think having a digital twin is a pretty common approach. I'm sure that many of you have digital twins. Not all companies have digital twins, and sometimes the digital twins are not as accurate as they should be because it takes a lot of work to do it well and so on. So, but if you have a digital twin, I would certainly recommend that you use a digital twin if it's accurate to do all sort of experimentation. So, and then you take it into production. We do see tuning in production that happens directly in production a lot as well, and that's also fine if you do it carefully. And I don't know if this answers your question, Mayrash.
Yeah, we don't have digital twins. I develop on production, so I don't know if a solution for that. Any more questions? So I do have a question. You showed a couple parameters, right? Like random page cost and that kind of stuff. And that describes essentially the capabilities of the hardware. And the usual story about query planning is that we have a cost model which describes the behavior of the system in sufficient detail. And then you set these parameters to reflect the reality. And based on that, we do the correct decisions for like query planning, right? And the same thing essentially applies to maximum number of parallel workers for the query, right? The parallelism and that kind of stuff. That also reflects some sort of capabilities of the hardware. The question is, when you see the tuning, the automated tuning, would you describe the result as like being a better reflection of the hardware capabilities in a way that the person couldn't tune, right? Like in theory, you could run a simple benchmark, you would measure what's the perfect value of random page cost, and then you would set that. But the other option, the other possibility, of course, is that we are making other mistakes in query planning, like we are estimating the selectivities and so on. And therefore, your model, like the automated tuning essentially overshoots and picks a value, not that actually perfectly reflects the hardware
Fix the planner, basically.
but kind of like compensates for the mistakes that happen elsewhere. Like, which of those is actually more like true?
Right. So this is a fascinating question. I have at least 3 answers I want to give, so I'm going to try to make it short. The first thing, it's something that you said, the results of the tuning should reflect the hardware. And you're basically defining a mapping function that goes from hardware to this decision on the parameters. That mapping function, I don't think it's well known. And so, and also there is some planner kind of assumptions on how to create that planning, that function, right? And so I think that even if you were trying to do, even if you wanted, since that function is not well known, it's a latent function somehow that you can kind of estimate some things, maybe guess some things, but you don't have the function precisely, then it would be really difficult to just do this from on a piece of paper without having this trial and error type of loop. The second part on the planner, I think the planner, of course, is a beautiful piece of engineering, but it has perhaps some limitations today. And I think you guys have been also thinking about the future developments for the planner. And I will argue that we need to tune Postgres today. So if we are fixing the hardware by right-sizing the parallelism, for example, or the disk access and so on, or we are fixing something that comes from the planner, this is still a win, even if you overshoot, as you said, to kind of fix, compensate the planner aspect itself. If that gives you a better tuning of the system, because you're basically kind of fixing or patching the planner on the fly like that, I think it's still a win at this moment. When the planner will be better, you will not do that anymore, right?
Yeah, I mean, like, if I may, that wasn't the question, right? Like, the question is, like, I don't argue that it has a benefit.
No.
I'm just asking which of those actually it is, right? Like, are you getting closer to the actual hardware value, or are you compensating for
right
that?
So
I don't know.
Let's go on a specific example. If you're doing the parallelism, the worker parameter, so that one highly depends. So you can have a big machine with a lot of cores, but sometimes using more workers, it does penalize you, right? So this is the parallelism paradox, or how it's called, right? So it's not always better to use more workers. And so in that case, even if the hardware has many more workers, it may, I have an example in the first example on the left that shows exactly that, for example, where the parallelism was basically sequential for the max parallel workers per gather, because that application would pay the price of having multiple workers working on in parallel for one query, right? And so in practice, what we see as well is that these parameters have an effect to each other. And it's very difficult to say, I'm going to just focus on this one, because this one will affect the other ones in a non-completely understood way. And so when you kind of look at all of them more holistically, you may end up changing multiple parameters at the same time, and this leads to a better outcome overall. In general, I think the direction that this takes is usually reflecting better the resources, as you say, so that option. But in practice, you may see some scenarios where you really need to wonder why that type of decision was made, and then if you do a little more research, you end up finding out maybe that that decision was a good decision, because now you have fewer temp files, and that really leads to a better outcome overall. Just an example.
I think that's a good point, that the parameters actually do affect each other in non-trivial ways, right? So for example, the maximum number of parallel workers, if you have many workers, then you probably don't need that much random IO and that kind of stuff, right? Because they will actually do kind of compensate, like do prefetching essentially, right? Good question.
We do see that sometimes parameters that belong to different categories, as you say, different memory, disk, and so on. Sometimes you need to increase them all both to achieve the high performance, or maybe the opposite. One goes up, and so there's a correlation analysis that can help for those type of things.
That is true, and the model is by definition meant to be a simplified version of the world, right? That's why it's meant model. So it will always have like inaccuracies. Any more questions? Okay.
Yeah, another question, you were showing these differences between pgtune and dbtune, right? And I was wondering, did you see a pattern that, like, if there were some parameters that pgtune got like consistently wrong, or that the db tuning got like consistently better in that case? Or like, was the contribution, was it like that some of the parameters were like, let's say, similar, and then just some were different, or was it really like different? Yeah.
So I think the easiest, I would love to run an analysis on that. That would be a nice blog post, I think, idea. But in general, pgtune will not know very much about your workload, or almost at all. So if you have an application like Opinions that I was showing, the one on the left in the first chart, it will probably give you a higher parallelism that you need, just because the machine has multiple cores that are available, and it's more natural to give a higher number of workers than a very small one. So pgtune will tend to get that wrong if your workload doesn't reflect the need of parallelism, for example. This is a very specific example. Yeah.
No, I think we need to wrap up,
okay.
Because the next talk is about to start in like 3 minutes.
Thank you.
Thank you for the talk.
Thank you.